In this video, I want to look at a review of component vectors. As I've looked at people's homework and how they were doing things, this still seems to be a big area of struggle, as people are not sure how to use component vectors, or you're not really using component vectors when I think they're easier, especially on some of those problems on the last homework. And I just want to kind of go back over and kind of show you how to do those with component vectors. So first, let's imagine we have a component vector of -2, 3. And we want to find the direction and the magnitude. So how we're going to do this is, if we think about a component vector, -2, 3, what that is we go left 2, we go up 3, and then that is the endpoint of the vector that goes to 2, 3. So what we're going to do is draw this right angle. Here is our 2, here is our 3. We want to find this resultant, and we want to find this angle. Now, many of you are still doing this using law sines and law cosines and all that kind of stuff, and that works. I just feel like that takes more work, and it takes a little bit longer. So I want to kind of show you how I would do this. I would find R by using Pythagorean theorem. So just use Pythagorean theorem, and that is 4 and 9. That's going to give me the square root of 13, which let's get with the decimal, I can just do that on the calculator, and the square root of 13 is 3.606. So my distance, my magnitude is 3.606. If I want to find the angle, I just do that with inverse tangent. So tangent is 3/2. Notice I'm not using the negatives here really. That doesn't really affect me too much, and you'll see how in a second. So now if I go to the calculator, I just do inverse tangent of 3 divided by 2, and I get 56.31. So that means that that angle is 56.31 degrees. Now, as I write my final answer, I will get 3.606 is the magnitude or the length, and my direction is this angle here is 56, so that is west 56.3 degrees to the north. So that is how we take a component vector and we convert it into the direction and magnitude. I don't think necessarily I did those enough in the videos I posted. I just got to this point and then just said, and then you end up down here, and I didn't go through it in enough detail. So I think as you do this, it doesn't matter if you use the plus or minus based on where this component vector is. You just need to think about your angle from what northwest it is from. So let's look at another example. Let's say I have two vectors, and I'm just going to use a force. So let's say I have a force of 2 newtons, and my angle is north 40 degrees west. And then my second force is 4 newtons of force, and this is east 20 degrees north. So doing component vectors is a much easier way, I think, of doing this, because you don't have to worry about your picture. So north 40 degrees west for 2, something like this. This is 40 degrees. This is 2. And then all I want to find is my x and y coordinate. Now, when you do this, what I'm going to show you here, you always want to use our angle to the x-axis, which is 50. Because now, to find my x, I just have cosine of 50 is x over 2. So that means my x is just 2 cosine of 50. And if I just go to my calculator, I can just do 2 cosine of 50, and I get 1.2 excuse me. Now, as I do all of these other problems, you will see we can do the same thing to find the y. It would be sine of 50 is y over 2, which ends up with just y equals 2 sine of 50, which if I put 2 sine of 50 into our calculator, I get 1.532. Now, once I've done that, you notice I am in the second quadrant over here. So my x should be negative, my y should be positive. So I think my component vector is negative 1.286, 1.532. So I had to switch this to be negative here because of what quadrant the angle is in. You know, if I drew an angle and it was down here, then both the x and the y would have to be negative. But when you make your angle to the x-axis, it doesn't matter. You're always going to have positive. So if I go to the next one here and I draw this vector, east, 20 degrees north, 4, here's 4, here is 20. Once you draw that vector and you think about, okay, and you get the picture drawn correctly and you have your angle to the x-axis, it's always going to be the same thing. My x is just 4 cosine of 20. My y is just 4 sine of 20. And if I do that, my x is 3.759 if I put that in the calculator, and my y is 1.368. So now my component vector here is 3.759, 1.368. So if you do it by component vectors, this form right here, x magnitude times cosine of an angle, y magnitude times sine of the angle, will always work once you have your angle drawn to the x-axis. So now, once I have that information, let's see if I can get this here. I can forget about those drawings. I can come over here, and now I can just take these two vectors that I get, and all I need to do is add these vectors. So if I add these, I get, this is 2.473, and this is 2.9. So now this is my new resultant vector. So we go back to what we did at the start. I can take that vector, forget everything else I've done, and now just go work with this vector. So I can draw, this is like the first problem I did. I draw this vector and I think, okay, this goes over 2.473. This goes up 2.9. And then now all I need to find is this r and this theta. To find r, it's just Pythagorean theorem. 2.473 squared plus 2.9 squared. You put that in the calculator, and I get 3.811. To find my angle, I use tangent of 2.9 over 2.43, and I will use the inverse tangent here on the calculator, and then I get 49.543. So my answer is 3.811 newtons, and then east 49 degrees 5, 4, 3 degrees north, and there's my final answer. So hopefully this shows you how you can convert it from component vectors when you have a component vector to get your direction and magnitude. And then when you're given the direction and magnitude, you just convert everything to component vectors, add them together. Now that you have your component vector, you can switch it back to find your direction and magnitude. Now I'm going to do this same problem. I'm going to take these two vectors here, and I'm going to do the same problem by drawing a picture and going through the whole picture by using law of sines and law of cosines to show you get the same answer. But I think this way becomes much more complicated, and especially what becomes much more complicated is the picture. I know many people struggle with the picture, so let me kind of go through this so you can see how I think this way is much harder than just doing it with components. So let's draw this picture out, and I'm going to try to use these lines here to try to make it a little bit easier than me drawing straight lines. Our first is 2 at 40 degrees, north 40 degrees west. So that means that this length is 2, and this angle here is 40. Our second vector is east, 20 degrees north, 4. So that goes to there. And then once again, this is 4, and this is 20. Now, if you were doing this at home with your protractor or trying to draw it, remember one of the things we want to do is we want to think of there being another north, south, east, west kind of grid right here to kind of help us get this accurate here. So now I'm going to draw my 2 again here, which is length 2 degrees 40. And to make my picture look nice, I just drew it there, but I'm going to cheat and you would just draw this here. And then we connect it to here, and we draw this line, and there is our parallelogram. Now, as we look at this, we have a few things we know. This is still 40. This is 2. And if we draw our resultant here across this parallelogram, from here to here, and let me change the color of that. Let's make that red and to there. To find that resultant, to find this R, what I need to know is I need to know this angle right here. That angle right there, then I can do law of cosines, which would be R is 4 squared plus 2 squared minus 2 times 4 times 2 times cosine of that angle. And then to find R is R squared, so I got to take the square root of the whole thing. So how do I find that angle? Well, here's a few other angles we know. If this angle is 40, I know this angle is 50. And this angle is 20, so I know this angle here is 20, which tells me that this whole angle over here that I'm trying to find is 70. Now, another way I could do this is I could come over here. And I know this angle is 40. I know this angle is 20. So I know this whole angle here is 70. So I know that this whole angle of this parallelogram here is 40 and 70, which 40 and 70 is 110. And if I subtract that from 180, that will give me the whole angle over here of this parallelogram, which is 70. To kind of help you see that, let me draw it over here for a second. Without our diagonal, our R, we have this kind of picture here. And if this whole angle here is 110, then I know this angle has to be 70. And that is what we have here with this parallelogram. So now we put that in our calculator with the law of cosines, and we get 3.811. Now, that just gives us our length. That's our R. The next thing we need to find is we need to find direction of R. So what I'm going to need to find is this angle right here, that theta, to figure out the total direction. So now I'm going to have the sine of theta over 2 is the sine of 70 over 3.811. And if I cross multiply, put that into my calculator, I get my theta to be 29.543. But now you will notice that that is just this angle, but I need this whole angle from east all the way up to the red line is my total distance, or my total angle, excuse me. So I have to add that 20 down here to the 29, which is going to give me east 49.543 north, and my length or my magnitude was 3.811 newtons, which you can see that is the same thing we got back here by doing it with component vectors. We end up getting the exact same answer either way. Now, as you look at both of these, hopefully I think the goal was to show you once we understand component vectors, they're so much easier and you don't have to do this complicated drawing. Now, I don't think it's a bad idea to kind of still understand a rough sketch of the drawing to make sure you kind of know the general direction. Like you can see here, I know the general direction should be into the first quadrant so that my component vectors should be in the first quadrant. They both should be positive. That kind of check my answer, so to speak. But so many people, as I look at your homework, still are relying on doing it with these drawings. And as you can see, these drawings get very, very, very complicated. A lot of angles, a lot of geometry things you got to remember. When you do it with component vectors, all you ever need is right triangles. And as long as your angle goes to the x-axis, I think it's so much easier to do it with component vectors. You don't need anything more than Pythagorean theorem and inverse tangent. And with those two things, you can solve all of these problems. Trying to get these crazy drawings is a lot more difficult. So hopefully this kind of helps. Hopefully this clears up some of the confusion and helps you understand how to do these component vectors and how to do these problems a little bit easier.